Hello.
Hello.
So, yeah, do you hear us, guys? If anything is wrong with the sound, if Metal Snake's voice is too low or not, like if the volume is not overall equal, please tell us so that we can fix that immediately. It's always terrifying, those 2K pages PDFs. Yeah, it's like playing StarCraft 2. You just have to get in there and play, you know? You don't read 2K pages, you read the table of contents, and then when you need something specific, you look at specific paragraphs, specific blocks. You don't read the whole thing. Salut Astro. Okay, so we're gonna start. So Metal Snake, can you just speak so that the guys hear you and we can make sure that everything is fine?
Hello. Is this volume okay? I think I might have moved the microphone a little bit, but I hope it's okay.
It's okay for me, and normally the parameters are the same as last time, so it should work.
Sounds good.
Okay, so just so you can see the current state. Right, I made a few modifications basically from here, I think. I added all these things from last time. It's not much, it's basically documentation.
Yeah, I saw on GitHub. Yeah.
So you can see a README and comments, basically comments. So the current state is that we have something that, well, builds. And we have this script that runs QEMU and creates a serial line or COM port on Windows, and we have printf. Basically, that's it. And so that's what's visible. What's not visible here is that we have code that handles interrupts, but only at the processor level.
I noticed.
So let's find something. Do we have a picture here? So
Hang on just a second. I think your stream is not showing the right stuff for
oh
now.
yes, sorry about that. It's not showing anything at all. Yeah. Do we have a diagram here? Maybe. Interrupt controller. Do we have something like this somewhere? I like to have a some data
Block
sheet
diagram.
with the controller visible.
I saw one with the 80 or 80, 86, and the
That one is okay. What we have here
that
is
works.
yeah. So it's from UC UCOS 3, which is a very small real-time microkernel. Well, a small real-time kernel. It's not really a microkernel. And this is the model they use, and it's quite accurate. I mean, it's the picture you should have in mind. You have the CPU, so you have to configure your CPU so that it receives interrupts, and then when receiving an interrupt, it leads to execution of some code, your interrupt handler. But then you also have an interrupt controller. And here, the thing is that you can usually mask individual devices, so you can block interrupts coming from them. And you have some services like retaining the state of an interrupt. So you have two ways of raising an interrupt, basically, which is edge triggered or level triggered. Um, Edge triggered means that you need an edge on your signal, electrical signal. So you need a change. Basically, the hardware is going to detect a change. Whereas level, it's not detecting a change; it's just giving you the current value. These are the two ways of doing it. So the problem with edge triggered interrupt is that if, for example, they are reset very quickly and it's out of your control, you might miss interrupts. Because if you poll, for example, at a frequency that is not the one used by the device, you might sample the signal at 2 times and see that there is no change. So the interrupt controller is usually the thing that prevents that from happening. It's normally wired to the devices in a way that completely prevents that. And then when it sees an edge interrupt, the signal can be reset to its standard value, and the interrupt controller would just have a flag somewhere that tells the CPU that an interrupt is pending. So that's the kind of services provided by the controller. Another is priority, for example. If you have multiple sources, you want to have nested interrupts because you really care about latencies and real time. Usually that's the job of the interrupt controller too. So here we're not going to work with a very complicated interrupt controller like one I've just, like a hypothetical one providing the kind of services I've just told about. We're going to work with the legacy XT PIC. So XT because it's IBM XT, so that's very, very, very old. This thing was made in 83. 83, that's how old it is. Except it's not exactly, like, it's the same device. So maybe we'll have a reference here. It's the same device, except we have two of them in the 80. So this one is from 84, really, wow. I thought it was from the 90s, 33 years ago. And yeah, it's this thing here. So 15 RQs from 8. 15, not 16, because one of them is used to cascade. That's normally the word used here. So we're going to have two controllers. That's important here. Well, that's important for Metal Snake because he's the one who's going to write the implementation. But basically, what it means is that here we have two controllers instead of one, but we are going to consider them as one unit. Okay, I'm going to leave the browser here for you. Okay, so basically that's what you have to do. You have to write a driver for the interrupt controller. You have to initialize it. You have to allow the installation of handlers. You have to raise handlers on interrupts. So don't be afraid. It's simple, really. And then the objective for tonight is that when we enter some data on the COM port on the serial line, we should have an interrupt. Like even if it's not handled, even if we have an empty handler, it should be fine. Let me read chat quickly. How does the CPU poll the interrupt signal? Is it between every instruction cycle? Yes. Well, it's the processor is driven by a clock. So yes, the clock drives many things in parallel, right? Every time you have a cycle, that's really what it is. It's like it says something might have changed. So basically, your state changes one cycle at a time. Sometimes longer because you have stalls, you have dependencies. You need to wait for data to arrive in. But yeah, basically you have one interrupt line on the processor. It's just a pin, a single pin, and that's this pin here, right? It's usually called the RQ or interrupt pin or line. And yes, it's polled on every cycle normally. Now I'm not a processor expert, so don't trust me on that because maybe some CPUs don't do that for power saving reasons, for example. Okay, but that's the idea generally. Okay, so well, you have the con Metal Snake. Uh, Go ahead.
All right. um, I need to hang on. I need to get the right website first on my machine.
Before we start that, I'm gonna guide you just a little. Find a name, create your empty files, make it build, you know, um, and maybe yeah, get your repository up to date too, because I'm not sure you have all the changes I did since last time. So make sure everything that is related to infrastructure is done before you start, okay? So that you can just completely focus on your work after that.
There we go.
So are you going to? Yeah, okay. I'm letting you do that first. Sorry. Yeah,
What's this?
you're not in the right location.
Oh, whoops.
It's a kind of mistake that's going to happen all the time, don't worry. Sometimes I work on X15 and I mean X1.
uh, it merge then? Or is it... Was git pull remote hello?
Pull should work, but pull from my repository, I think. Yes, pull, but did not specify branch. Yeah, you have to tell the branch. Master, basically, we only have one. Does not appear. Okay, let me. No, that's not the way to do it. Like this. Okay.
Oh.
And then you can push that, and automatically it will push on the remote branch that is tracked by default, which is your own on your repository. So yeah, you don't have to specify anything. Okay. So now you can try building, running, make sure that everything works, adding your file. How are you going to name your driver?
I mean, we're working on the PIC,
Okay.
so it's gonna be PIC.
That's one possibility. Another would be the name of the hardware device itself, like I 8259.c, well .c,
Okay.
and that way of naming avoid conflicts. So it's worth mentioning.
Okay. Well, then we'll make a wait. Is this like this to open up? Save the
Yeah,
it's like this.
this is in the background. Yes.
There we go. Okay. Yeah. Just testing. Sure. I 8259 sounds okay.
Okay.
I'll make the um, interface first. I guess I'll leave this here.
Well, the first thing to do is creating empty files, add them to Git, include the licensing, the inclusion guards, and having empty files, just so that it builds and everything is set up and you don't have to care about that anymore. So usually what I do is that I copy existing files as
Yeah.
templates.
Yeah. Exactly. Yeah. Um,
Yeah, something like this. The I here means Intel. I'm not
okay.
telling you to change anything, just for your information.
And go ahead and just work. Actually, no, we don't need this necessarily. Just need this part. Okay. Add that to Git. And then go back to the page. All right. Um, how does it work? You have to initialize it first. Here, it tells you about the RQ thing you said about the cascading.
Mm-hmm.
So RQ2 is used for the cascading, I guess, or is can't be used.
So
Um,
RQ9, um, when we say RQ9, we mean that RQ07 from the second PIC, uh, well, you have 8 RQs per controller, so 07 on the first, and then 8 to 15 on the second. So RQ9 is actually the second on the second PIC, which is wired to the second on the first PIC. Or if you can find something about that, I'll be surprised.
but this is for one of them. Uh,
Yeah.
I couldn't find them cascaded. I don't
Oh,
think.
there you have it. See? Here. This is the master and the slave.
Oh yeah. So the slave tells the master pick to or that it's interrupted. Then, if the slave has an interrupt,
Basically,
so if one of these lines is triggered,
yeah.
then it triggers the
Yeah, you will
master,
see it
which
as
then
interrupt
triggers.
too, so you will have to ask both your controllers about their pending bits. And
Mm-hmm.
if it only comes from the master, you can completely ignore the slave. But if it comes from the slave, you will also have to clear the pending bit on the master.
This one.
Yeah.
Yeah. Okay. Yeah. Okay. Um. So first we want to set it up, and I'm just trying to find where it was, but we need to send a command to it, essentially,
Mhm.
to
This is right below programming with the PIC. You have the master PIC command data. So these are the ports. Then you have
oh, here it is,
yeah,
initialization.
okay, yeah,
Yeah,
the initialization commands, yeah.
this code. And I couldn't figure out in the data sheet
Mhm.
why exactly that is.
It's many data sheets of that time are particularly obscure, really. So that's not surprising. Oh yes, there's an A. That's right.
Name?
Yeah, it's so. I'll be taking the mouse for
Oh, A.
now.
Yeah.
Quickly, I was referring to that A here.
Yeah.
Let's see. So mhm. Interrupt sequence. No, I don't think it is. Content of second interrupt vector byte. No, that's not it. Initialization command words.
Mm-hmm.
Okay. So what are you looking for exactly?
It was the it says here that you need to initialize the pics with code 1.1,
Okay.
and I couldn't find that necessarily in
Okay.
the
So
fact
command
sheet.
words 1 and 2, hoping we do start with 1. Okay. Whenever a command is issued with A00 and D41, this is interpreted as initialization command word 1. Okay. The edge since circuit is reset. Okay. The interrupt mask register is cleared. Okay. Okay, so words 1 and 2. Page starting address of service routines. Oh yes, they have a mode that is called paging. That's annoying. 8 request levels will generate calls to 8 locations. Okay. The address format is 2 bytes long. The 8-byte interval will maintain compatibility with current software. In an 86 system are inserted in the 5 most significant bits of the vectoring byte. Okay, so I think this is what it is here. Do we have um, third interrupt? Yeah. Where's the word described? So we have 8-bit words, I think. And basically, yeah, this is a matrix of registers and bytes, if I'm right, or even bits. I'm not even sure
Okay.
because they don't say here. It's not clear. Before null operation can begin, each in the system must be brought to a starting point by a sequence of 2 to 4 bytes timed with the odd pulses. Okay, not WR. And then we have operation command words. Okay. So D4. They say D4, so this must be it, I think. Well, D4 can be that too. Interval. Um, yeah, you're right. It's so I
A
did
little
this
weird.
again. I did this a very long time ago.
Yeah.
The PIC code. So yeah, it's really not fresh in memory. So we're looking at why the first command word has this value, right? This is what we want to know
Hmm.
from the data sheet and not just OSDev because we trust them, or maybe we don't trust them that much.
Exactly.
So
Yeah.
yeah, this is really cryptic. So yeah, the level and edge that I was talking about earlier. Call address interval, then I have no idea what that is. Single means that this is the only. Okay, so we have this bit to 0. Yeah, because we want to have 2 PICs, so we'll have initialization, control word 3 and 4. So those apparently may be set, but I don't know where they are. Usually you have something that describes those bits. You know, you have like something like this, or rather
So
something like this here, or this, which is
hmm.
set. So maybe it's after that, but that would be weird. But who knows? Oh look, I think this is where it is. Initialization command word format. So this is where it is. 0. Then you have your 3 bits here, which are the interrupt vector address, but only in a specific mode, and I'm not sure that this is the mode we're using. Pretty sure it's not the mode we're using, because we're using this mode here, because that's what we have. We have an 8086 system, well, compatible with the 8086. Then level or edge, this is entirely, like you can only know that if you read the AT specification. So here, for example, do they say anything about that? No. So they say level triggered. Okay. But I really don't know. So I guess this is a case where we can only trust that kind of resource because it's really not clear and well specified and not easy to find and like real modern data sheets. So let's say level. Then we have the call address interval. So yeah, again I don't know what that is. I suppose it's 8 because this might be bits, but this is pure speculation. We'll have to read what call codes are, I think, or call intervals. And yeah, I don't know what that is. So maybe it's even further in the documentation. Masks, yeah, reading, so that will be for later. Sorry, edge and level trigger modes. Mhm. They don't say anything about what should be used with the 86 mode, unfortunately. Cascade mode. Yeah, so that's what we're using, cascade mode, okay. But they don't mention anything about the initialization that I could see. By 2 only, okay. And then it's nothing important for the software side. So it's really only this for now. Continued, okay. That's the
Focus
one.
is
Call
initialization.
address interval. Okay, I don't know. Cascading mode. Okay, this is 0. And I see W4 needed, that's probably 1. But I know that from memory. You
Yeah.
would have to read more to really be sure about the values of the bits. But basically, that's what you should have, right? That's what you'd expect in a datasheet.
Well, that
Something
was
like this, and then the bits.
the ICW4. That was because of uh, we're using two.
Yes. So it specifies the mode here. So I know that we use 8086. I'm sure of that, but again, I can't tell you how. Like it's basically probably because of OSDev again. Um, Auto EOI. So EOI means end of interrupt. Hey, when did the stream start? Hello, Michael C. Not long ago, like maybe half an hour, roughly. Um, and then, yeah, buffered mode, non-buffered mode. We have to look at that too. I think it's non-buffered. I don't think we want to buffer anything. We don't want to introduce delays when handling interrupts. Special fully nested mode, not special fully nested mode. Again, we'd have to read about that, but we're pretty sure we need forwards. Slave ID, okay, so that's easy. We just have 1, zeros, and then on the last 3 bits because you have 8 interrupts, so 2 to the power of 3.
Okay.
So basically, you can encode anything between 0 and 7 included, or 8 not included in 3 bits.
Yep.
Okay.
I think in that first.
Let's not worry too much about that. Like we have the specification, we have found some things about it. Okay, we're basically happy with what we have, which is a combination of the datasheet plus what we have on OSDev. The datasheet alone doesn't say how the PC is wired to the controller, which is why we need external resources like OSDev.
Yep.
So we can trust that and just write the driver.
I think this one, by the way, this because this is the first code that you send.
Yeah,
This is 1 because we're
yeah,
using 2. This one is that looks like a 1 to me.
it is a one. Yes.
So that is why it's 1 1.
Oh yes, probably yes. So everything else being 0, yes, we want cascade mode. So yes, probably the call interval would be 8, but again, I'm completely speculate on that. What I don't understand is that here we have edge triggered. Let me check in X15 how I do that. I'm doing it on my laptop.
Okay. Is the end of interrupt, is that basically handling the flag?
Yes, the pending bit, yes.
Okay.
So in my implementation, ICW1 is only 1 0,
1
which is
0.
yeah, which is
Okay.
weird because it means it doesn't make sense. Oh wait, no, it's not. It's 1 1 like you. It's just that it's ORed and I didn't see it. So there is one bit which I called init, and then there is IC4 to indicate that we are sending a false word of initialization.
Oh, right. Okay. Okay.
So apparently it's See, this is something I don't understand. Just to take the mouse quickly. Level triggered edge mode. So this here is clearly level. When it's set, it's level triggered. So here we have 0, which means that we have an edge triggered mode, which is what I remembered from when I worked on the APIC. Okay,
But is that actually set though in this?
it shouldn't be used. Yeah, it's not
Okay.
used. Their code is actually quite good.
Sorry, what is quite good?
Their code here is
Oh
decent.
yeah,
The naming,
but
the macros.
you can definitely see what's going on. This is kind of what you did.
Yes, exactly.
Yeah.
Except I use or instead of plus, but that's very close.
Yep.
Plus just handles the carry bit. That's all.
And
Well,
maybe we'll
more than
just
that,
get
but
to the vector offset. We'll have to read about that because I'm not quite sure. Is that
yes.
for
Okay, so
the
here,
cascaded one then, or
no, the vector offset is probably. Um, wait, do they call? Do they actually call it somewhere? Masking? No, they're not initializing it. So what's yeah? What are they calling offset here? Vector offset for master PIC. Okay, so this is the vector offset. Do you remember what a vector is when handling interrupts
it's
or exceptions?
essentially a table, or I see it as a table,
Okay,
kind of, or an
it's a
array.
table. So this is the index in the table of the handler for basically RQ0. It's an offset. So what vector is going to be used for RQ0 and then RQ8, which is the first of the second, the first RQ of the second PIC. This is why you have two offsets.
Oh, okay.
So it's very simple. I'm going to open the big document from Intel, which is this one. Oh yes, I
Okay, go
didn't
ahead. Go
mount.
ahead.
Sorry. And wait, in the code you should already have something about this. You should have CPU H, maybe. Let's see, do we have anything about interrupts here? Not yet. No. So we have handlers, but I think it's a default handler for everything, if I'm right. Yes, that's it. It's the same handler for everyone. So basically, the vector is the index in that table.
Yeah, yeah.
Okay. And you can see that here. Let's see. System programming guide, interrupt and exception handling, vectors. Basically, this is the table of vectors. So from 0 up to 32, so 31 included, it's exceptions. These are vectors reserved for exceptions or just reserved not to be used. So you can, what is usually done is to map the legacy PIC to 32 and then 32 plus 8.
Oh, okay. Right. So since these are the peripherals, these go into user, where we're gonna be
Devices,
handling.
external devices.
Yeah. Okay. Yeah.
So when they say the user
That's
defined
fine.
here, the user is actually the one who uses the processor directly. So it's the OS developer.
Yeah. Yeah.
And actually it's also the hardware, the device developer. Because the OS developer usually does not assign interrupt himself. Some devices can be assigned, like can be programmed to have a specific interrupt, but usually what's done is that the hardware tells you how it's plugged. This is done with ACPI. ACPI is basically the specification for the PC currently. And what you do as an OS developer is that you write code that reads tables, and more than tables actually. You have it's some kind of interpreted bytecode that you run, and that code, among other things, tells you where the device is. So its interrupt, its mapped addresses in physical memory, and anything else that a driver would need to use the device.
Okay. I'm gonna leave this one open for now. The only thing we really need to do, I guess, is start the PIC, and then later.
Yes, for now, yes.
Yeah. Okay. Since this is called I8259, would you then call this the
Yes.
like this as
Yes,
well?
I'd like the project to use the
Setup?
same kind of namespace rules that I use in X15. So yes, that's a good name for it.
Okay. And for now, that's pretty much the only thing we're going to be doing.
Namespaces are very simple in C. They don't exist. You make them up. But if you don't,
No, but
you risk conflicting code.
I was thinking you might want to call it PIC setup.
Well, no, it's consistent with the file name, so.
Okay.
It would be very confusing not to have the namespace matching the file name.
Okay. So initializing it, we want to set the words.
Mm-hmm.
This is basically what we're doing. I'm not sure what this is called. Remap.
No, I don't. So
But
the remap is probably for the vectors. That's the only thing that might really change here.
so you could, yeah, when you're setting this up, you could give
Because
your
that's what it
custom
is. It basically
offset.
maps uh, a hardware interrupt, an external interrupt, to an internal vector, and that's mapping. So this is why someone would call it remap, but I don't like the name.
Yeah.
Remap would mean that it's already initialized and mapped, and that's probably not the case. It's probably disabled.
Also, that is probably, since it's called remap, this is needed.
Oh,
You're
right,
saving that,
yes. Yeah,
and
we don't
then
care about that. We can
yeah.
just completely erase the values. That's right.
Okay. So um, these are actually, we're missing a couple, I guess. Maybe not for this one, but we're missing the words to.
Yes. But
Uh,
actually, the words too, as you can see, there is no reason to have macros because it's the values themselves. Well, here you could have a macro to say that it's RQ2, yeah, but
yeah. Okay.
here, for example, just writing 1 shifted by 2 to the left, and 2 being a macro like cascaded RQ, for example, would be enough.
Sorry, what was that? The last bit?
Here, for example, you see that they need comments here to say what they're doing. Like I regularly say, when you write a comment, first thing to do, ask yourself, do you really need the comment? Here, it's quite obvious that 2 is the cascaded RQ, and 4 is 1 shifted to the left by the cascaded RQ. You can see that here.
Oh, yeah.
And here, those bits actually completely match the hardware device, if you look at it. See, this is just a register. So 000000100. That's exactly the value that we see here.
Oh yeah. Yeah. Okay. Um, and I believe you also had an IO. Uh, is to write write bytes. But to which port? Um, Take command. Oh yeah, that's up here. So these. Oh, so these are the I/O ports for the master and PIC slate.
Yes.
Okay, gotcha. Okay. And these would be. Um, these wouldn't be public, so they would be in C.
Mm-hmm.
Oops.
Don't forget the namespace.
Yeah.
So one problem with this kind of naming, I8259 as the namespace, is that it doesn't really make sense for someone who doesn't know. But as soon as
Sure.
people know that your policy is to name your files as the hardware, like your drivers, the same as the name of the actual hardware, it becomes quite easy. That's what Linux does mostly. It's not a strong rule, but it's applied uh, very often. Also, let me just check one thing quickly. Okay, very good. Now, those zeros are not really... Oh, we can do that. That sucks. Not really needed.
Okay, so um, these are the master slave ports. Then okay, yeah, it's the same thing.
Yeah, it looks like the same.
For now, what is
Honestly, you can just copy them as a reference and then change them as you need and remove those you don't need. There's no reason,
yeah,
like,
because
unless it's really a lot of code, and by doing that, it makes sense that the copyright applies for a couple of lines that anyone would have to write anyway. It makes no sense to waste time. And here you can even remove all the comments. I will write them when I have time off stream,
okay.
like I did already for a couple of files.
Oops. Sucks that you can't use the blocks.
Yes, it's annoying. We probably can, but we don't know how. You need you need to add the namespace though
Oh,
before aligning. I mean, it would have been better before aligning. And you should start with filtering those you don't need. Like level, we know we don't need level. Actually, in ICW1, we know we only need 2 bits.
But this one basically only says this is the bit which is either level or edge. So if you want to clear it and set it to edge, then
Yeah, but we
I
don't
mean
need to do
initiate
that.
0. Yeah,
We don't need to
yeah,
do that. It's really a strong principle that I encourage people to follow. Don't code things that you know you don't need. Or actually, the right way to say that is only code things that you know you need. Otherwise, it's
okay.
just over engineering, and it's one of the recipes for bugs and extra cost and bad results, basically. You should code expecting that your code might be changed to have more features, so make it really maintainable, readable, understandable, but don't implement those features you don't yet need. That's useless and counterproductive even, most of the time.
Seems fair. So these are not ones
Oh, we're
those
going to
aren't
need them. Maybe, I don't know. We'll
they're
see.
not used in the example at least, I don't think.
Well, at least
Oh,
the
okay.
8086, this one is important. And we
That's the
can
only
probably
one that's used.
just use that, like keep that one only because obviously the rest, we don't want buffering, we don't want an automatic EOI, clearly. We don't want the specially fully nested things, no. So yeah, it makes no sense. Namespace. Hmm. Okay, good.
There we go. And in this document, you can see there's IO wait, and
Yeah,
these says you need that on older machines. And
yes.
since we're using,
We can completely forget about that.
yeah, okay,
Like these machines are so old, I'm not even sure any of them currently works. Nobody uses them, so well, maybe that's not true, but they are not going to change their system anyway. Students who use this code are not going to have them somewhere anyway.
fair enough.
It just complicates things for nothing really worth.
Okay, so the next is the second word, which is the offset.
Okay, so that's a little more complicated. How are you going to do that before you write? Tell me so I can tell you whether it's a good thing to do or we should do it differently.
Um, well, it starts because this one maps to the what we just saw, like 32,
Hmm.
starting 32. Um,
What I'm
you have
asking is an
a
architecture
define,
question.
just how do you mean architecture question? Are we gonna do this?
What name are you going to use? Where is that name going to come from? May it be used somewhere else? You know, because you could
Um,
just write 32 and it would work. And I would say that it's absolutely not the right way to do it.
well, this relates to the IDT, doesn't it?
Yes,
So it makes sense to have 32 as a sort of as an offset there.
no, it makes sense. That's not my question. My question is where are you going to write that value? So, for example, um who owns that value? Who owns the IDT? Who is responsible? When I say who, I really mean which module, but who who is responsible?
Well,
Uh,
that's
do you think it's the
I
PIC?
guess the interrupt controller. I guess.
No, it's the CPU.
Oh, okay.
See what I mean? Because
Uh,
if you need to use uh, other values from the same set of values, like other vectors, uh, you can do the same. You can write the value directly, but then if someday you have conflicts between those values, like you use the same at two different places, you don't know. So you need to make them, you need to separate your code into modules which have a clear purpose and responsibility, a functional, like a single functionality. And here, like what you really want to avoid is crossing functionalities in the same code. You have to do that because you want to combine functions, but you have to do that at precise locations. And everything that doesn't need multiple functionalities should only focus on one functionality. So you don't want to mess up your interrupt controller with your interrupt table inside the processor. These are two separate things, and it's really easy to see in that image. You have one code that manages this and another
Oh,
that
of
manages
course.
that.
Yeah.
And then you have another that manages that, right?
This makes this little block diagram makes a lot uh,
See? Yeah.
more clear. Yep. But the interrupt table.
We don't have any right now, so you'd have to create it.
Oh, okay. I thought you'd maybe done that with the
No, no, no.
ADT stuff.
Like I said earlier, all the interrupt handlers are the same. So currently there is absolutely no uh, nothing about vectors except the IDT size, maybe.
Okay. We're gonna have to. We're gonna want. Where is it? Oh, this one. All of these.
No, we don't need to.
Or
Well, at some point we may
at least an
want.
offset.
We may yes. We may want to add a few of them, like we'd like to handle maybe some kind of exceptions. I don't know which ones. If we had paging, we'd want to handle page faults. But basically, we don't need to handle anything. Like if we had debugging, we might have to handle a few. Like there are two, I think, two vectors related to debugging, but we won't do that. So we don't need. So you can call them that, but you should also insist for the user who reads you on the fact that these indexes are interrupt vectors, interrupt and exception vectors. Or you can do the reverse. You can say that there are these things are interrupt and exception vectors, which also happen to be indexes in the IDT. So you need to carefully like you need to think carefully about how you describe that, how you name that, so that people who read you quickly understand you and with as little ambiguity as possible.
This doesn't really say anything, or well, to me at least. I'm not even sure if this is correct.
It is correct.
Yeah.
Vectors are literal indexes in the IDT. They can be defined that way. So we have to say that they are both exception and interrupt vectors. Because on Intel, the same table is used for both. Okay, don't worry too much about the comments. I'll make a pass and review them anyway. So you could call that vec, for example. No, not user. Why user? Because it's called that way in the specification?
Yeah.
Yeah, but
Well,
like
I
I
mean,
said, the user
always gonna
is
be user. Yeah.
it's the user from the point of view of the people who make the processor. So it's not a good word for us here. Vector is a better word, yeah. So vector, whatever. It doesn't matter much. You can't call it that. There isn't a single vector. You could call it, for example, vect underscore PIC0.
Oh, we're assigning. Okay, we're assigning these as. I thought it was just an offset, just to get like the user space and then add whichever.
No, because then the problem would be the same. Where do you list all the vectors that are used? And how do you make sure that you don't have a conflict? Yeah,
Okay, so
one,
we
two.
master
I
slave.
usually count from 0.
Oh, there we go.
And it's not 32. Yeah. No. How many interrupts do you have per PIC?
Oh, 8.
And yeah, you could do it that way. It's even better
There we go.
because then you only have one macro to change and everything changes accordingly.
Okay. We have to include that.
Oh yeah, and you don't include IO either, by the way.
Oh, that is true. Do you have any convention of having the own module inclusion, or do you just add them all in one big list?
The policy is usually direct inclusions. So basically, don't count on your header to include things. If you
No,
need
okay,
them,
but I
include
mean,
what you need.
I meant style-wise, like you have it
No, no,
alphabetically. But yeah,
it's among the others.
okay. Oops. That is not the right thing, I believe. Pick one data, offset. So pick master with offset.
That's data, not command.
Oh, oops. 1, 2. Okay. This was the
Mm-hmm. So you need a macro that tells
shifted.
you which RQ is used to link the master and the slave. We don't want to
Yeah.
hardcode these values that way. So you can call it like RQ cascade. Okay. The reason I write RQ first is because you can have other names for special RQs, and when naming, you always want the bigger namespace first. So the first would be the name of the module, then you would have the name of RQ, because you might have multiple RQs, and then the actual name of your RQ inside that internal namespace.
Yeah.
It's a very good way to easily avoid naming conflicts. No, you only have a single one.
Yeah, but the other one was shifted by
Yeah,
someone,
well, you
right?
can shift it in the code.
True. That does mean you have to know why, though, right?
What?
I mean, seeing a shift doesn't necessarily explain what it does or why it's shifted.
Well, the only thing that can explain that is the specification. So we'll just link the specification, and people who read the specification normally should understand that. No, it's 1 shifted by. Here you shift 2 by 1. That's not the same thing. But again, I will take care of the comments, so that's okay.
Oh yeah.
Yeah, it's good. It's good.
Yep.
I think it's good.
This also goes to data.
Have to check, but I think that's true. Yes. Okay.
Pick 1 data, and then pick 2 data.
Now here, I'll probably write comments that will be very similar to what we have on the OSDev for the same reasons, because it's an educational kernel. So instead of just telling people go read the datasheet that no one understands, I'll probably write some text that tells the same thing as they do on OSDev. I mean.
Yeah. Okay, so these are all the. Actually, no. This is IC. This is the 4th word. Just have a quick look.
Yeah, this one is very simple. It's all zeros except the last one and the first one.
Okay. But this then is not enough, right? Because you also need the 1.
Actually, I'm surprised that. Oh wait. Let me just take the mouse. The mouse. Sorry, quickly. This bit here is supposed to be 1, but I don't think you can write it. Just check quickly. The special freeness in is programmed. Okay.
Seems to be 1 after the first word. Looking at the other words.
No, I mean this one.
Yeah.
Wait.
No, I mean.
Oh yes.
0.
Okay. It's actually not for us. Okay, because these are the 8 first bits. This one is outside. Okay, so it's probably for, I don't know, the hardware probably.
That makes sense. Just checking. Write those to both. Right. So that should be the initialization done.
So we have one last thing to do. It is initialized, but we need to set masks. See, that's what they do at the end.
Here.
Above, restore save masks.
Oh, here.
Yeah. So here they restore masks. What we could do is just set all interrupts masked for now.
With some parameter, but and this is something we're not going to be like, this is something internally, so
Until it's needed outside, yes. And one reason to use the namespace on all your symbols, including the internal, the private ones, is that the day they become needed outside, you don't need to change the name.
that's true. Yeah, actually smart thinking. So we actually need to know how to set the mask.
Oh yes. So
Which
the
before you do
data
that,
the data port is actually called the IMR port, the interrupt mask register. So basically, when you write a 1 in that, the corresponding interrupt line is masked.
yeah. Okay.
And you have 8 interrupts per controller. So
Um, how do you exactly write to the IMR though?
well, like you did it in your code.
Really? Oh, this is IMR.
Well,
Or
no, the data port is IMR.
can you see that? Oh,
You may
wait,
not
sorry.
see
So you
that
write
here.
the data.
Yeah, maybe, but there is a bus, so you can't see that here. Uh,
Oh, sorry.
See here?
Yeah. Oh, exactly. Yeah. Okay. Gotcha. Um,
See here, the PIC has an internal register called the IMR, 8 bits wide. Um, and yeah, they only tell you that, well, they don't say it explicitly, but in the code you can clearly see that they use the data register, the data COM port. So basically, writing to that COM port sets the value of the internal register.
okay. That's basically what you're doing here as well
Yeah,
then.
except. I wouldn't. So come back to your code, please. I wouldn't do it that way because here, so you can actually have a function called set mask. Yeah, you could have that, but what you will eventually need is a function set or a clear masking bit. So you'll need two functions: one that writes the mask completely, and another that just reads it, changes the value, and writes it back. And what you could even do to make things simpler is to actually store the values, like cache them in memory.
Okay. So this name of these it says it's gonna set the entire thing, but
Okay.
you're saying we should. No, but what you're saying is what you're gonna need eventually is you're gonna need one that sets individual lines.
Yeah.
Okay.
Preserving those that have already been set or cleared.
Yeah, which is basically this reading.
Yes, except, like I
Part
said,
of.
we don't want to read, modify, write every time. We could just keep the value in memory and only change that and write only. Never read.
Okay.
Because when you initialize, everything is masked. So you know the value, you don't have to read it.
True. Uh, okay. Then I'm not really sure what you want me to do.
Okay, I'll do it. Quickly, very quickly.
Yeah.
Let's use the mouse. I'm not used to using the mouse. Oh, wait. So I have two mask global variables. And here you would write them basically.
Okay.
And you need to, well, now it's your job to come up with a nice interface for your function. Also, setMask being private should be static.
Yeah, I saw that as soon as you
Yes, and
said
just
this.
one thing quickly, very quickly, because it's the coding style enforced in the project.
Oh, yeah, of course.
That's it's a very little detail, but I care about that. Sorry.
It's actually kind of smart because it's you save with essentially
Mhm.
you have all your keywords. It eats up your space.
It makes reviewing very easy for me, at least.
What did you say?
It makes reviewing the code easy.
Ah,
You
yeah.
can easily identify both the type and the name of the function, and you have space for packing lots of arguments if you need to. So everything that goes too far on the right, which is basically everything beyond 40, 50 characters, is things that I might just skip when reviewing code because I consider them not important. A review is usually superficial, really. So, is that the only thing
And
you
this
need?
is no, uh, because I feel like this is gonna be pointer to
No,
this,
no, 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 no. No, no, no,
or
it's
you
not
mean the
pointer, it's just a
static?
copy. It's okay. No, what static? A static argument? What is that? No,
Uh,
it's simpler. Remember that you have two picks.
yeah.
So you need to set the mask of one specific pick. Like I said, I don't know how to call your function here. I just know that you need that argument. But that doesn't define the way your function should be called. You should add something.
Oh, you mean name-wise, or
No. No, 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 no. How do you know with this interface to which pick you are setting the mask of?
well, that depends on your argument, right?
No, it doesn't.
'Cause-
You are setting the mask of a pick, but you don't know which one. You need an identifier, something. Like here, when you
yeah.
code like, forget this, okay? This only
Yeah.
means that we need to pass this variable. It doesn't say anything about the rest, okay? Here, how do you know to which pick this applies? How do you know? Like only restricting yourself, oops, to this problem here. Every function solves one problem. Your problem here is setting the mask of a pick. How do you know which pick?
Uh,
No, 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 no. Restricting yourself to the function.
and
You don't.
I'm not really quite sure. No.
You need to add something. You need to add an identifier as an argument. You need to let the user tell you which pick must be referred to.
Okay.
And since we're doing object-oriented development, you should probably start creating an object for your pick.
But what exactly? So we need an identifier. So it's gonna be uh some struct. But what we're adding there is it's either it's just a one or a zero basically, or a
Well,
counter of
you
how many
have,
picks you have.
yeah, like, if you really need an object that is multiple properties in a structure, basically, yeah, in this case, you'll want a structure. Here, a simple identifier might work. I think that's what I do in my code. But you would put that identifier first in your arguments in place of a complete object. That's what I'm saying. Because here you're about to write the identifier as the second argument. So again, I'm
Yeah.
nitpicking, but it's a way of thinking that is consistent across all the code I write. So I
You
insist.
mean you added first this one here?
Yeah. It's basically a very simple object. You don't need it to be 8 bits though. The reason for
Then
the mask to be 8-bit is because it's going to be serialized to the PIC. But here it's pure code, it's purely logical.
and since we only have two, you could use a bool, maybe, or would you use a bool in this case? What I don't necessarily know like whether
Bool.
a bool
No, bool
uses
means
it.
true or false. So here I
Yeah.
just use an unsigned int. The reason being that it's an int, it's an integer, so you use the int type by default, unless you need something like larger or smaller. And by default, you should make as many variables, integer variables, unsigned as you can, because um, operations on unsigned integers are very well defined in the standard, whereas signed integers, not so much. There is some implementation defined behaviors with some operations, especially when you have like bit shifting operators involved.
Okay.
So here, if we really wanted to have a structure, for example, wait, I don't understand why you have a variable for the ID. Why do you have a variable? What do you intend to
I don't
use
know.
that variable for?
As soon as you said we're gonna make this object oriented, I thought
Yes,
we
yes.
needed
So
to create something.
let me say that again, hopefully more clearly. You have two ways of doing that. The the dogmatic way would be to create an object, so have a structure, for example, and
Hmm.
you would have an accessor to get the structure depending on some identifier. So we'd have a function, for example, I8259 uh, get, for example, that would return an object, and the argument would be an identifier. And then you would pass that object to set mask, and for example, that object would contain the address, like the not the address, but uh, the values for the command and data ports for that PIC, maybe a Boolean flag whether uh, that says whether the PIC is the master or the slave, for example,
Oh yeah, yeah,
things like that.
yeah.
You could do it, and it might make sense, and it might even be better. I don't know. Here, we're not doing the full object-oriented solution. We just have an identifier as our object. So we don't have a structure, we just have an ID. But the ID is the same, right? It's like a this pointer. It's just a reference to something.
Okay.
But you know
How
what?
about you?
Let's do it with a struct actually and see how it goes. Let's
Okay.
do it the full way and because
Um,
it's usually like it quickly becomes more handy than you expect at first, very quickly.
you can easily add on other stuff essentially. Uh, I haven't worked with it quite a bit though. I see you use constant struct in here as well. Construct,
Uh,
and I'm not quite sure how
maybe,
that.
maybe, but write your object first. Everything starts with the definition, like start with your data, and once you have a clear idea of what your data is, you can write the functions. No, no type def, no type def, no, 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 no.
Oh,
Sorry, that's against
doesn't
the
make any
coding
sense.
rules. No const, it's just a definition. Const would be for a variable, not for the type itself,
Okay.
except if the structure contains const stuff. But that's usually not the case. No, that's not how you write it. You probably use typedef too much, and you're used to that. Uh,
Yeah.
it's close, but that's not it. Okay, and yeah, that's it. Okay.
Okay. So we have the that unsigned ID.
Hmm. Do we really need the ID here? Like, we could simply have an array, and the ID would be the index in the array. We could have that.
Okay. Yeah. Things that are, let's say it's a master or slave,
Hmm.
which that could be bool. Um,
Yes, so std bool
hmm.
immediately. And just one thing, because I'm, again, very nitpicking,
Oh, yeah.
that no, no.
Oh,
Uh,
master is
yes,
true
that's
or
better.
false. Yeah.
Type,
Okay.
like, what is a true type? That doesn't make sense, But
Yeah.
is it a master? Yes. Is it a slave? Yes. Is it a type? Doesn't know what it is.
Exactly. Uh,
It's it's actually a semicolon. Yes. So you could have the command too, like the command and the data ports.
so this yeah address basically.
Yes, and we could even refactor the setup to use that object at some point.
Okay. And again, unsigned int, right?
So here, actually, these ports are used by IO write, and you can see that they are uint16t types. Because again, it's like the hardware in the form of in and out instructions on the processor require that size. So we really want to prevent any user or maintainer of the code to even have a slight chance of writing a bigger value in that.
Do we need the port on here?
Yeah, sure.
Oops.
I mean, need maybe not, but I think it's better. That's actually, I think in my code I have the same problem. I don't like I name them the same way you do because I probably saw the same code. But uh, if I would write that now, I would add port in the names of the macros to let people know that these are IO ports. So why did you move master? Out of curiosity.
Um, uh, because I believe the biggest, you want the biggest types at the front essentially to do with
Why?
adding it.
How do you justify that?
Because I read it somewhere
Okay.
essentially. Yeah.
So yeah, it's
I
probably
don't.
about structure alignment and layout. Structures are aligned to the the alignment of the member with the biggest alignment, basically. So if you have a 32 bits integer in your structure is going to be aligned to 32 bits. Like when the compiler generates the the, the data in the object file, it's going to assign an address, a relative address, which will be 4 bytes aligned. And then the linker, when allocating for that variable, is going to do the same because the object file contains the information that tells the linker to do so. And this allows the compiler, for example, to generate code that assumes that such structures are always 4 bytes aligned. So, for example, this means that the compiler will not generate more instructions than needed. And on an architecture, for example, that requires aligned accesses to memory, if that assumption is false, you get a bus error. You get an exception basically. So so this alignment thing is quite important. Like this is one of the reasons why C is so handy when dealing with hardware, is because you can actually predict the layout of your structures, and you also have macros, well, attributes, compiler attributes, to control that. Like we use pact in the CPU code to force the compiler to ignore any alignment. Like pact basically tells the compiler that the structure might be completely misaligned. And so any access created by the compiler, any access in the form of instructions, must take that into account. All instructions must be valid even if the address is not aligned. So that's one thing. And so if you have small values like a bool is basically 1 byte. You cannot know that. It's implementation defined. It could be 4, it could be 8.
Hmm.
Usually it's 1 because that's what makes most sense. So if you have something small at the beginning of your structure and then you have something bigger, you have a hole. Directly, you have a hole because your members, oh, that's something I didn't say. Here, if you have 2 bytes, this means that your member will be 2 bytes aligned. This one will be 1 byte aligned, probably. We don't know. Like, we can't know for sure, but it's likely. And so the whole structure is going to be 2 bytes aligned. And if you put bool master at the beginning, because the structure is 2 byte aligned, and this must be 2 bytes aligned, the compiler will have to add a hole between those two members. And that hole is going to consume memory. And this means that if your structure gets a little too big, it might span over a complete cache line, for example, which means that when accessing your data, you're going to retrieve 2 cache lines, where if you did things differently, you might have needed only one. Here you still have a hole, but the hole is at the end. You don't see it. But basically, it's like having bool unused. It's the same.
Yeah. Yeah.
One reason, for example, is that if you create an array of PICs, uh, the first one is 2 bytes aligned, the second one has to be 2 bytes aligned too. So the size of one object, the size itself must be 2 bytes aligned, right? So that the next structure and the next after it in an array are also 2 bytes aligned. So you have this unused thing at the end, but that's okay because you don't access that. You access that, you access that, and you access the master bool here. So maybe if that's on another cache line, which it should not be, but if it is, since you don't access it, uh, it's less likely that you will need another cache line access. So that's why they usually say to like to minimize holes, and when you have them, push them at the end. Sorry for the time it took.
No, that's really good information.
There is a tool, by the way. Let's just show it to you quickly. PA hole. We don't have debugging information. Oh, wait. Is that because it's a 32 bits? Ah. Okay, doesn't work here. I'm going to show it here with X15 if it's compiled very quickly. By the way, you can see there is an error here. That's because of a mistake in the makefile that I have forgot to fix for 2 weeks now, I think. It's not critical, but still. So here, for example, this is the output of the tool PA hole on my kernel. And this is the kind of things you can see here. The size, the number of cache lines it takes, the number of members, padding required. So let's look at an interesting one. Elson's data, for example. You can see holes in here, right? That's probably because the alignment of this one, which is 8, apparently, which is likely, as soon as you have a pointer, um, your structures on 64 bits are going to be 8 bytes aligned. And here the spin lock is only 4 bytes, which is perfectly normal because we want our locks to be as small as possible. So the compiler has to introduce a hole so that this structure remains aligned correctly, right? And then you have holes, well, a bit everywhere because this is a big structure and it's not optimized yet. And here it tells you about the cache line boundaries.
Oh yeah. Yeah.
Let's see another one, another interesting one. So you can see, for example, that here, which is a structure about an ACPI table, it's not packed. I don't think it's packed. And you can see here that there is no hole, absolutely no hole. And this shows how C is reliable when using structures to serialize data with memory. You can do that. And this structure is the same whether you have a 32 bits or a 64 bits compiler. It's going to be the same. Can I find an interesting one? I don't know. Most of them are quite simple. Yeah, thread, but again, thread is big, so that's expected. Um, yeah, CPU. Yeah, basically, yeah, cache lines, holes. It's the same thing. And you have padding at the end, but here it's not pad apparently. All those structures apparently are not pad, but that's maybe. Oh wait, yeah, okay. There is some unused space in the last cache line, which is reported by the tool too. I don't see padding though. Ah, padding 7. Okay. So yeah, see, we have a bool, but here we have physical addresses which are 64 bits, so we need 7 bits of padding. And then we have 24 bytes left in the cache line because we expect, I think the assumption here is 64 bytes cache lines. But you might have 32 bytes cache lines. So, but that's one good way to examine your binaries and make sure that the structural layout you have in mind actually matches what runs on your machine.
That's really just to check or mostly to check the alignment then.
Yeah.
Okay.
And then obviously when you allocate data, you have to take care about the alignment. So for example, malloc, if we look at the man page for malloc, we should see something about it. No? Okay, it's here. It returns a pointer to the allocated memory which is suitably aligned for any built-in type. So basically on 64 bits it's going to return you a block which address starts on an 8-byte boundary for that reason. And the compiler can count on it. But if you have stronger requirements, like if you want to align to a cache line, then you have POSIX mem align, I think, which allocate aligned memory. And this is usually a requirement in kernels. So it's good to have like your structure which fits nicely on a single cache line, but if it's not allocated and to an address aligned to an 8-byte boundary, to a cache line boundary, it's going to span over 2 cache lines. And then you're going to have potentially 2 cache misses instead of 1. So the whole chain must work for this to work.
Okay. That's good to know though, but it's some of that information is also a little in depth, I guess, and requires
Yeah,
reading.
it is. Just use the occasion, the opportunity to talk about that because it's, I think many people don't realize the underlying reasons behind packing data, alignment, all these things. So if that helps remove some of the cloud around that, it's all the better.
Fair enough. That sounds good. Okay. With this, we can.
So one other
There's
thing
no
we could
ID.
do here, one thing we could do, we could remove that and put that here. So it's 8 bits, so we can put that here. And now you have a pretty good object here.
Except, well, you can ID it by the port, I guess.
No,
Maybe.
because, well, we could, but there is really no need. We just need two identifiers, 0 and 1. So maybe you want me to write that because, yeah, I think it won't be. Uh, Looking at the time, it's better that I do this part. So this is
Okay.
what I'm going to do. I'm going to create objects. Well, I'm going to implement that object for you quickly, very quickly, like set mask maybe, and maybe the refactoring initialization, and then you'll do the rest once you understand the logic behind it. Okay?
Sure. Yep.
Okay. So here we want static initialization. We can't make it read-only because we have to change the mask. Like everything else doesn't change. It could be read-only, but the mask does change. So we don't want a static const array. So here I create an array, and here I statically initialize the structures in that array. So here is one way to initialize structures. And then we just do almost exactly the same thing for that, except here it's slave. And here this is false. Okay. And now one thing we might do would be this. ID maybe. Like these macros, like maybe we don't even want them. Maybe we just want to pass the raw values. Like they don't really make sense. So let's implement an accessor that returns a PIC from an index. First thing, let's make sure that our index is within boundaries. So we're going to use assert. Do we have assert, by the way? It's here. Okay. So these are standard headers provided by the compiler or the environment, and these are kernel headers. Assert is both, to be honest. It could be anywhere. It wouldn't matter much. But I think we've used it that way elsewhere, so I'll keep doing that until maybe I change. That's not very important. The important thing is here, using the index and making sure that it's included, like it's a valid index. So it must be less than, strictly less than the size of the array. Okay, so now we need array size, which is a macro here, macros h. What did I do? Was
I
that
didn't
you?
do anything. No, no. Hands off the keyboard and mouse.
Okay, that was weird. Maybe I may have done like a vim command instinctively without realizing it. Okay, so macros gives us array size. So here we know that the index is valid. Okay, so now every time we use that accessor, we have the bonus of having bound checking. Also, you can see that here this algorithm is the fastest we can have. There is nothing faster than a simple addition. Whereas if you had the index inside the structure, you would need a for loop with a potential linear complexity until you find the pick you want. So that's why usually when you can do it that way, it's better. Now here, let's refactor this. So we have, we don't have those IO writes directly in that code. Okay, so I'm going to write the code directly here and then only move it. We probably do need them both here. Okay, like something simpler. Write command, for example. So you can see where I'm going with this, I suppose.
Yeah. Yeah.
Like, instead of having those names, let's have something even more meaningful.
Wouldn't the function just be I8259 write command
Sorry?
rather than pick right? Wouldn't the function just be I8259 write command rather than pick write command?
The namespace I use here
Or
is that of the object.
oh, yeah, gotcha. That makes sense.
That's how I make a function in C a method for an object-oriented usage pattern. So here we could also rename that pick master, for example. Okay.
I guess in this case, yeah, since there are only two picks, we can just use master and slave.
Yes,
If there
and
would
we
be
can
more
even
than
have
two.
aliases for those functions, so that we don't even know that master is 0 and slave 1, right? It doesn't make sense.
Yeah.
Okay, so here... Okay, almost done. Okay, so here we're giving low-level access to the setup function. We're giving it access to the command and data ports directly, but that's something we don't really want. Usually when you have objects, you want to encapsulate. So here, for example, we're not going to write that. This goes away because the variables themselves don't exist. And here, set mask, we could let it that way, actually. But set mask, for example, we could have something else that we could call apply mask. And we could have another function that just sets the mask without applying it. And we don't even need to have such a function anymore. We just need a function that clears or set a single bit in the mask and then applies it when we're done. This way we can change multiple bits without communicating with the device, which is slow. And then once we're done, we apply the mask, a single, just once. Okay.
Which is enabling the mask, or what exactly is the
Well,
difference
let's
between
write the
applying and
functions now.
Okay.
Well, the methods, really. So first, this one. So this one is going to be iowrite pick, I think it's command port, okay? And the byte is here. Okay, very simple. Okay, and then would have apply mask. Okay, so this one. So applying the mask is writing to the data port the mask that is already set inside the object. Also, you can see something here. You can see that we don't change anything. So these pointers can be const.
Ah, right. Okay.
This tells the compiler that the data used here doesn't change, so the compiler is allowed to reorder things around because it can rely on the value remaining the same. You don't really need const here because all your functions are static, so it won't change anything with regard to optimizations because the compiler knows its entire compilation unit, and it will see that nothing changes in those functions, so it will add the const itself internally for optimizations. On the other hand, if you really want your object not to change, const would be useful. And here, yeah, maybe we don't want it to change, maybe we want it to change, but we don't like. If you don't care here about the object to not change, to be immutable, you can you can forget about the const keyword. It's just that I have that reflex, but really here it won't change anything. The generated code should be exactly the same. Okay, so I think we have that. I'll just create aliases here. Okay. And if you wanted to do it really really elegantly, I think it's probably the best, the most elegant way, and you can't really do it better than that. It would be something like this. So let's find a good name. So PIC ID master, so slave here. Okay. Master. Okay. So now we can create RDs.
Why would you use
You'll see. You'll see.
functions? Okay.
Oh, the functions. You'll see. You'll see. Functions are always a superior way to access data because they can change while keeping the same interface. If you access arrays directly, you can change the access without changing all call sites, all use sites actually, because they're not call sites. So for example, if you want to debug, if you want to set a breakpoint, if you want to add counters, because you have functions, you can do that easily.
True. Yeah. Okay.
That's what encapsulation is really used for.
You see, with the function that you had before, the get pick, why not just use the defines that you've just added?
Here?
Yeah. So.
Okay, I'll let you do math.
Here you had get pick 0
Mm-hmm.
and get pick 1.
Okay.
Why not just use the define as a parameter?
Oh, I could. I could.
Than...
So yes, I wanted those to hide the define, but then I realized that I need the define for something else, and you're going to see why.
Okay. Okay.
So let's copy it.
Oh, right.
See?
I didn't know you could do that. Okay.
Yeah. This way, if someday you want master to be 1 and slave 0, that's okay. You don't have to change the array.
That's really cool.
Okay, so that's one thing. So yes, you're right. Now these functions make little sense because the macros themselves are enough to provide the meaning. So that's what we're going to use. Okay, and see how the code is, see how different it is? It's got more abstract. You don't really need to care about ports anymore. Like, you want to send commands and data,
A
right,
lot more
to the
visual.
master
Yeah.
and the slave. And it completely abstracts addresses and values. Like here, it's like I said, you still break encapsulation a little because you allow the set of function, which is a static global function, to have a raw access to the content of registers. But the reason I keep it here is because maybe the order here matters. Maybe you can't just one single function initialize master and then another function initialize slave. Maybe the order in which it is done matters. I mean, you need to do something on the master, then on the slave, then on the master, then on the slave. See, you can't just do all on
Yeah.
the master and all on the slave, I think. Maybe you can. I don't want to waste time. It's late enough. It's good enough that way. Here, on the other hand, it's clearly high level. Apply the mask on the master. That's it. You don't, like, the problem of how you apply the mask is completely moved away.
Yeah.
Here, like you have the logic, and here you have the implementation, and each problem is clearly separated. And here, when solving that problem, you don't need to solve it for the master or the slave. You solve it for a PIC, and then it works for both. So you have reduced your problem, and that's how you avoid bugs, makes things simpler, go faster, etc. So you have your base. Now you can continue to build on top of that.
Okay. Do we need enters or new lines at the end, by the way, for C files?
Sorry.
Do we need new lines for C files, by the way, at the end? Or
Oh, let gedit do the, like, forget about the problem.
okay. Um,
So it's quite good. It's really good. Now we want to do one thing. We want to test our interrupts. So we'll need public accessors to enable and disable interrupts on the PIC.
on the picket, okay. Which basically is the applying of the mask or disabling.
Well, yes, we change the mask and we apply, but now we'll have to take care details about whether the RQ is on the slave or the master, and what we need to do in which case in both cases. But for now, just like remember, uh, for the user, so for the developer who uses your header and your public interface, the PIC is considered a single entity. The
So
details
this is
of whether you have a master, a slave, or whatever are hidden, encapsulated in your implementation. So basically, what you want to provide to the user is the most simple and compact interface you can come up with.
which sounds to me like it's just a setup. If you can get away with that.
Well, no, because the setup masks everything. So here you want to do two things. You want to enable interrupts, and then you want handlers to be called for those interrupts. So the handlers will probably be handled by the CPU module because uh, the CPU module is responsible for the IDT, and the handlers are in the IDT. So here you only want to allow or prevent interrupts from the external hardware, the PIC, to be routed to the CPU. But you still need to provide that. Like the the CPU module is probably going to be your only user, right? Probably, I don't know, maybe
Mm-hmm.
not. But you still need to export some functionality to that external module. You need your public interface to provide more than setup. Like you need at least enable interrupt, disable interrupt. And let's call them RQ maybe, because that's the usual word for external interrupts.
But uh, in here, you're also this is the interrupt. You have some interrupt enabling and
So
disabling
those
here.
ones are on the CPU. They're
Okay.
internal.
Okay.
They control one bit in the status register that says that the CPU receives interrupts or not. That's all. It's completely uh,
Global
yeah,
interrupts.
it's completely different. The functionality is completely different from what you're doing now. Right now, again, refer to that image here.
Yeah. Yeah.
This is what my functions apply to. This is what your functions apply to. It's completely different.
Yep. And by enabling the RQ, you're basically changing the mask, is what you're doing.
Yes.
And you only have 8. Uh,
So you shouldn't.
Lines.
Can we think this way? I don't think you can think this way. You could do that. You could use that type, but I think it's a mistake because that type still encodes for a lot more values than you really need. Um, you basically need to enable, well, to control RQs between 0 and 15. So you'll have to check the input value anyway, and since you do have to check the value, there is no point enforcing an input type. And because you're not serializing it to memory, there is absolutely no reason to use such a fixed width type. You could just use unsigned int again, because that's the default type for integers, and you'll have to check that anyway, like with an assert or with actual error checking, depending on how you want to handle that kind of error. It depends on your point of view. If you expect users to never make mistakes, like if they make a mistake, it's their fault, it's their responsibility to always give you proper values, then you use assert, because assert might be compiled out, right? If you expect your user to, well, on the contrary, if the contract between you and your user is that you are responsible for checking whether the values are correct, you will want to check the value and return an error, and this will not be compiled out. But then it makes the interface more complicated because you return an error. So
And then the user
normally,
needs to
yeah,
do something
the
with the
error
error.
needs to be checked.
Yeah.
Yeah, you still need names for your arguments. You can call that RQ. Yeah. Now, there is a small problem on the Intel because the same table is used for both interrupts and exceptions. And when I say interrupts here, I mean RQs, external device interrupts. Here, RQs start from 0, but in the vector table, they start from the value that we have. And by the way, let me quickly
32. Yeah.
change that while I think about it. Yes, it's this one. So how did we
Oh yeah,
name that?
master
PIC
and
master and
slave.
PIC
Right.
slave. Okay. Okay. So again,
And the
now that this is done, we don't care about the value. We only care about the semantics, the name. Okay.
yeah,
So here, um,
the
this start from
RQs are
0.
yeah.
Yes, but
So they're
RQ0 means vector 32, vector
yeah,
for the master.
exactly.
Okay, so you have to take care of that translation. And again, the fact that you're doing it here internally in your private implementation code completely abstracts that kind of detail from the user, who doesn't have to care about that anymore. The user just gives you RQ0 and he has RQ0. That's it.
Yeah. Um,
in the header file too.
sorry, what? Oh, here.
The names, yes.
So you want to see if this is below.
That's one way to do it, but there is a more clever one, which would be to find the PIC for that RQ, and if it's null, you assert that it's not null. Because you will have to look up the PIC for this RQ anyway, so.
Okay, so you add. Um, I'm not sure. Okay, so you have your IRQ0, which.
It's not only 0, it's 0 up to 15. So for example, if you have RQ0, it's the master, but if you have RQ7, it's the slave. So you need to get your PIC object from your RQ. You need to look it up. So we could have, for example, here a function named getPic from RQ, right below getPic. Here getPic could be named getPic from index, but since it's the first one we wrote, the index is implicit in the name, I mean. But here, since our lookup key is going to be an RQ, we need to mention that, and that's why, for example, you have functions named get host by address, get host by name, for example.
Okay.
It's not an index; it's an RQ. So that's the first thing that needs to change. And so, how are you going to find your PIC?
Well, if it's 0, then.
No. If it's 1, how do you do?
Uh, but you're gonna need this, the offset.
No.
Right?
No.
No?
That's not how you look up your PIC. Remember, you have two PICs, they're cascaded, they're 8 RQs each. So from 0 to 7 and 8 to 15. So it's very simple. If it's between 0 and 7, it's a master. If it's between 7 and 15, it's the slave, and otherwise, it's null. And you don't need that check here, because the only thing you need is an index that you can then pass to the function right up, the getPic function.
Oh, right. Okay. Um, but you said so if you had if statements that adds.
You could use a switch here. I think that, like, do we have ranges on C? I think GCC has switch ranges. But you could use if. Let's just use if. It's simpler. Yeah. So another more elegant way to do it would be, for example, to encode the range in the object. We could do that, but not really needed because we have only two objects. So why?
Actually. One.
Ah, yes. Okay. So here, on the other hand, wait, because you are writing a hard-coded value, an immediate value really, with no meaning. Someone reads this is not going to understand why it's 7.
True. Do we have anything for that? I don't think so.
I'll just write it quickly.
Okay.
We can use this here. For example, actually we could use that. And that would be enough.
Number, okay. Gotcha.
And here it's actually correct to have strictly less than.
Yeah, because if you had the 7, it would not
Yes.
include the last one. And so here...
So that's not the coding style. Sorry about that.
Oh.
Yeah,
There you go.
it's the one true brace style. It's actually called the one true brace style, even if it's not.
Well, it makes sense. Saves a lot of white space.
And lines. I really like that lines get compact, you know. Yeah, you could do that. You need the right macro now.
Also return.
Yes.
Um,
The macros are above at the beginning of the file. ID master and ID slave. And actually, instead of index, we should call that ID. Let me quickly change that when I'm thinking about it. Done.
Your else's look like this, or do you add a new line?
Usually, so else, no, else is, the idea of the coding style is to have as much compaction as we can. So that we can cram as many lines as possible on a single page. But it's not right, it's not else. Because if you have RQ 1300, you should not return the slave. You should return null. I'm seeing some braces inconsistencies. Yes, functions are not blocks. They're not the same, and it's historical. It's basically the Kernighan and Ritchie coding style. So yes, there are some inconsistencies that we can happily live with. That's okay. But I agree with you. It's not consistent. So Quesadilla Quantum, that's a special name. Hi, what are you doing right now? So we are writing the interrupt controller driver for a very small educational operating system. And that's it. Yes, I understand satire.
Also need
No. What did you do? You're multiplying 8 by 8 here. The number of pigs by the number of pigs. That makes no sense. You only need to multiply it by 2.
Yeah, I have multiplied by 2. Oh wait, is it the wrong?
Yes.
Number of number of IRQs now.
Oh, sorry. But that's wait, is that right? Yes, actually, that's right. Sorry, my bad. Brain fart happens. Can you use parentheses to make sure, like, to clearly show that the multiplication has precedence over the comparison? Thank you.
What do we return if we don't get anything within that range?
What would you return?
Uh,
What's the pointer value usually used to say that something went wrong?
return 0.
Well, no.
Or nil.
Yeah. So just, yeah, stdef. Yes, you're right. We need stdef. But KNR actually uses the style I have here. So So then you are being inconsistent. Questa di la contum. Well, actually,
Okay.
there is no implication that you're using the same style as Satar because you learned from KNR, but that's the assumption I'm making by reading that. So here we're gonna do something simple. We're gonna use assert. The user is expected to give us sane values.
At the start,
Well, no,
does it matter?
and you should understand now why I wanted you to first look up the PIC and then to write the assertion. If you had to write the assertion before looking up the PIC, you would have to write that kind of thing inside the assertion, like assert this basically, right? But since you have to do that anyway to look up the PIC, now the only
Oh,
thing you need to check is this,
okay.
and
Ah,
this makes the code more common and the whole code more elegant. Well, after really.
because you don't get the nil. Otherwise, okay.
And you can write it like you can write it just like this, which semantically means assert that the PIC is valid.
Okay.
That's how you read it, in an abstract way.
You assert that it's not nil,
That's the
essentially.
implementation way of saying it. The semantic, like the high-level abstract way of saying it, is that the PIC is valid.
Okay.
Otherwise, and that's something I used to do in the past, I would actually write the check against null. But I talked with friends who convinced me that what we do here, which is called Boolean coercion, is actually good practice in some cases, like this one. It wouldn't be like it's actually mentioned. I'm going to quickly show you very quickly in the coding style, which is here. Boolean coercion. You have basically so this one is valid. This one is not. Like if you have an index and you know that, for example, yeah, black is 0, and you use Boolean coercion to test against a specific value which is not a Boolean. Like cannot you can't say if this color is valid, right? That makes no sense. This basically means if this color is not valid, print black. This is the this is what the code means, and you can clearly see that what the meaning doesn't match what the code actually does. The code should be if color is color black, then print black, and
Yeah.
then it would make sense.
Yeah.
And code that doesn't match, like if the meaning of the code doesn't match what the code actually does, it's bad code. Because then people have a harder time understanding it. And it leads to error prone code where maintenance might create bugs instead of solving ones. So try to make your code as meaningful as possible.
That's easier to say than to actually do. It's a lot of
Yes,
practice.
especially in C. But it's
Um,
possible.
oh yeah, just takes practice. Um, okay, we're gonna have to look at what we actually need to do to,
No, we
because
know
you need to.
already. We know already. Basically, you just set or clear a bit in the mask and apply the mask. That's all.
Because it's the same as this.
It's actually the same as this here, which is already implemented. So you don't need to actually write the code. You just need to write the logic. But you'll see that it's not as simple as that because of the
Oh, but
cascading thing. You'll see.
this. This is enabling. Uh, I forget. I thought it was setting. But
No, 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 no. The code already exists. What you need to do is write code that makes meaning. Do you want me to show you?
yeah, go ahead.
Okay.
Uh,
Well, it's actually,
then,
sorry. That would be the call. And actually we need our object as the first, like this is basically the this pointer in object-oriented languages. And then this is an argument for the method, which is enable RQ for the object i8259 pic. So let's write that function, that method. So here it cannot be const because it's going to be changed. I'm going to write it for the master only, because you'll see that for the slave, things get slightly more complicated. So very simply done. We enable, sorry, enable RQ, okay. So we enable, which means that we clear, okay, when a bit is set, it means the interrupt is masked, so it's disabled. When a bit is 0, it means the interrupt is allowed to go through. So we want to clear the associated RQ. So we want to create a mask, basically, okay? We already have the mask. Now we want to just set the bit for the given RQ to 0. So this is AND equal, basically it's an AND, we want to create a mask, okay? So we take the complement of 1 shifted by RQ, is that right? If you have RQ 0, for example, it's going to be 1 shifted by 0, it's going to be just 1, okay? And then you take the complement of that, which is everything but 1, which means, oops, which means that all the bits in mask will remain the same, because x and 1 equals x, except the very first one because it's 0. So now the first bit in there is going to become 0 too. See?
mhm.
And then done.
Um,
One thing we should do though is make sure that the RQ is less than the number of RQs here. And now you can see that there is a problem because we might give an RQ that is bigger than that if it's intended to be for the slave.
true. Yeah.
Just reading chat quickly, how do you feel about assigning values in if statements? Again, there is a rule for everything. And the rule here is, I'm going to keep that page open. Is it open here? No. The rule would be side effects and conditions. Conditions must never be made of expressions with side effects. This completely removes the need to think about short circuit evaluations. There you go. I think he did it in the string part of X1. Yes, that's legacy code, so maybe there are a few uses in old code. Like I'm pretty sure that these string functions date back to 2004 or 5 actually, so they're very old for me. No, in if, in while, it's the same. It's the same. He could even increment inside the while too. Yeah, yeah, but no. When you have been beaten by what compilers might be allowed, well, what compilers are allowed to produce and might actually produce, I'm talking about the generated code here, when you have expressions that get a bit too complex and that are not clearly defined by the standard with regard to sequence points, so read about sequence points in the specification, um, you don't want to be beaten ever again and spend hours or weeks on such stupid problems. So I completely forbid, normally, like expect legacy code, which is excused by default. Side effects in condition evaluations is completely forbidden, and that's a very like some rules are relaxed. If you don't uh, comply completely, sometimes it's okay for pragmatic reasons. This one is a strong one, so I should rework. I should update the string code because of that. Like I wasn't born with all the rules, so I had to come up with them with experience and usually failures. So now you can write, before writing disable, because we want enable to be complete before we go to disable, which is be completely symmetrical. Do you see the problem with the slave?
Yeah, because this goes up to 8.
That's one problem, but it's not the only problem.
Um, you also have the RQ.
Yes, you also have to enable RQ2.
Yeah.
So you have multiple strategies. For example, probably the best one would be to have inside your PIC object, and this is why an object is very nice for such things. You could, for example, imagine that in the object, you add a member variable that stores the number of enabled interrupts in that, like just a counter. You could also count the number of ones in the mask. You have special built-in functions and instructions to do that, like FFS, which means find first set, and not for fuck's sake. And if that thing returns you a valid index, it means that you have a bit one set in your integer. You could do that. It's very fast, and it allows you not to keep a counter, which is more expensive. Like you need more instructions. It uses memory, etc. So you could do that. And for example, if the mask has a single bit, like I'm actually stupid, if the mask is not 0, is enough, right? If the mask is not 0, it means you have, no, not 0. If the mask is not -1, right? -1 would be all bits set, right? So it would be uint 8 -1, like written like this. Okay? This is the same as 0xFF here. It's exactly the same. Right? Do you see that?
Yeah.
Okay. So basically, if your mask is different from this value, it means that you have at least one RQ enabled. And so if in your slave there is at least one RQ enabled, your RQ2 on the master must be enabled too. Otherwise, the RQs from the slave will not be redirected to the master and will not be redirected to the CPU neither. Well, either, really. So that's one way of doing it. The other way, which we'll probably do because it's simpler and it works, is to just keep RQ2 enabled all the time on the master. This way you don't need to care much. It makes the code simpler.
Yeah.
So let's just do that. Like in the setup function, you just change the mask of the master so that it actually includes RQ2. It enables RQ2, and you can do that with the method directly.
With this one. But how does this work? If this is over 8?
Well, you'll have to decide that too, but one problem at a time.
Okay. So before you enable the...
Well, no, because here, look, enable RQ here uses the mask. So wait, actually, yeah, you're right. The mask is set here. Okay, so you could change the value here actually. That would be okay too, but probably a little more difficult. I'm doing it here. Yeah, it makes sense actually. Okay. So now, okay, now we have this other problem of
Well, you can see which is which because of the.
yeah, you can do that, but
Mhm.
maybe you don't want to do that. Remember, when you write methods, you want your methods to write to work for all objects. You want to minimize specific code, especially in the methods. The one goal of having methods is to have common code. So if you have special case, you don't have common code. So basically, you have the choice. Either it's the responsibility of the PIC object to handle the RQ and shift it as necessary, why not? Or it's the responsibility of the user, which in this case is this static global public function, to realize that this RQ is meant for the slave. But here, since we use an accessor and we don't know what PIC we have, and we don't want to know what PIC we have, it's probably best that the RQ be handled by the object itself. Yes. So the assertion must be changed, the function must be changed to shift the RQ as necessary, etc., etc. And by the way,
In
wait,
the method.
wait. You're right. You wrote 2 here. That is not correct. You must have the reflex of making your code meaningful. 2 is not meaningful. That is meaningful. Enabling the cascade line, that makes sense.
There we go. So what you said was to not do it in this function, but to do it in the method.
Yeah. So basically have the knowledge in the object as dictated by the principles of encapsulation.
Um, we'd have to check if that which kind of pick it is.
Yes. And we have a flag in it for that, exactly for that.
But would have to, this will have to go.
Maybe not.
Okay. Because maybe you can shift the IRQ.
Yeah.
Okay. Uh,
But maybe like what you want is the end result to be valid. Do you really need to change anything if it's the master?
is the master, is that from 0 to 8? Oh, that
To
is, of
7,
course.
yeah.
7, yeah.
No, it's actually master. Like you can't change. Well, you can change the name of the member, but you have to check the name of the
Oh,
member.
whoops. Whoops.
Okay. Here you need another assertion. You need to
Okay.
make sure that the RQ is not for the master. Because you're going to shift it. So for example, if your RQ is 0 and you shift it, it's going to remain 0. And this is wrong, you know? Like normally,
Okay.
let's take a look at this because we have a problem here. We look up from the RQ, so normally this is correct. Like this is the pick for this RQ, and this code knows it, but this one doesn't. Maybe here you pass it a hard-coded value, it doesn't know. So what you could write, for example, is something like this: assert if it's not the master, it's the slave. So it has to start from 8, right? So assert that the RQ is greater than or equal to the number of RQs. Now here, the problem is that, for example, your RQ could be very high, could be 2000. But that's okay, because here you test that it's actually under the right value. So what you do here is that you shift it. So how much do we want to shift it? Well, maybe not shift it, it's actually just minus, wait, like this. See? Wow, this editor. So here you make sure that the value is not for the master. You shift it. So I don't want to say shift because I thought shift and then I wanted to actually shift bits. But basically that's it. You remove an offset to have the value as it is in the space of a single PIC. Like the space for both PICs is 0 to 15, but the space for a single PIC is from 0 to 7. So this is what we do here. And now if the value is too big, this assertion will catch the error. And then you're done. You have the right PIC, the right mask, the right RQ, you apply it. Like this as specific code go is fine. You know, it's probably as little specific code as we can write, because we want to avoid specific code. We want to write as little as possible, be as productive as possible. So yeah, but sometimes you have to, like in such cases. So here is probably a good case, like a good example of how to minimize specific code. Okay, so now you can write the disable function, which is completely symmetric.
Nearly identical, yeah. There was something about IRQ9 which is mapped to IRQ2 or something.
Yes, I didn't understand that completely either, to be honest. Do you remember where it was? On
It was on OSDev.
OSDev? Okay.
Sure. Yep.
Oh yes, here.
This one, I think.
Here. To confuse things more, RQ9 is redirected to RQ2, so when you get an RQ9, the signal is redirected to RQ2. These two chip architecture. So let's see. Where was it?
Maybe cascaded PIC. Maybe we can find it there.
Yeah, but where was the picture? Do you remember what it was?
Oh.
Okay, this one here. Yeah, this one is good. RQ9 is redirected to RQ2. I don't understand that. And it might be crap. I don't know. Either it's crap or it applies to modern systems with ACPI, for example, or really an APIC architecture.
Okay.
Because the APIC architecture allows compatibility with the old PIC that we are programming. And in this case, I've seen weird things with RQ9 indeed, but I don't know why exactly. I have to. This is still a gray area for me too.
Okay. And in this case, we only need.
Well, this has to remain for the same reasons, and it's actually disable RQ. Yeah.
Oh, right, of course.
That's fine. But I don't want. I don't understand why you want to remove that code here. On the contrary, it should be made like a single function. But we will do that some other time because it's already late. Let's try and finish. I'm not sure we're going to we'll be able to actually input something on the UART, or maybe very quickly. Maybe I'll do that so that we can finish relatively on time. Yes. That looks fine.
Yeah, that's it. Disable it.
Okay, well, that's it. Well, you have to write the global function that uses it now.
Oh, of course.
Okay, I think you're done. So let's build that. And I think you forgot the makefile modifications, but they're pretty easy to do. And I'll write the necessary code in the UR driver so that we can test the PIC driver. So what I'll do will not remain, it's just for testing. We'll write the input support for the UR driver sometime, I don't know when, but not today. Just a test today. Wait. It's still my nitpicking.
Oh, sorry. I totally forget that.
When you start to have many files, having
Yeah.
them sorted is just easier for the brain. Especially when you review. Because when you review, you don't necessarily know what you're looking for. Always start with the first errors, because there is a good chance that the other errors uh, actually depend in a way on the first. So here the structure has an incomplete type. What? Array index in non-array initializer. So I'm going to do that because I may have made a mistake.
Is it? No, I don't know how that sort of notation works. To be honest.
Field name not in record or union initializer. Really? With a port mask master. Okay. Is there a mistake above? No. Is that file saved, by the way? Yeah. Okay. Is everything saved? Yeah. Uh, that's weird. 0, yes. An expansion of a macro. I think it's that. Like, let me check. Where have I done it? Oh wait, in the thread module, I think. I have a big structure of scheduling classes somewhere. No, not here yet. Okay, it's here. Oh, maybe I need to, yes, maybe I need to give the size of the, okay. So let's move that definition here. Okay, and we can have that one here. And I think I need to do that. I need to tell the compiler how large it is because the compiler cannot infer it itself. Yeah, that looks better. Is it? Wait. Maybe it's not. Did we forget a thing here? We have std int, we have std bool. Static struct. Like, is there... Sometimes you have control characters that mess up the interpretation of the compiler, but that doesn't seem to be the case here. So I'm going to check again. Ah, shit, the keyboard doesn't work in VNC mode. Like, I can't maintain a key pressed and just wait for it to act.
Annoying.
So what's the difference? There's a const here, but I don't think that changes anything. And this here should be 0. And here we have equal to, yeah, bracket, then we have the members. it's a comma. My bad. I think I told you it was a semicolon.
No, that wasn't the struct. The regular struct.
Is that better? Doesn't seem better for some reason. Why is it incomplete? Like, is there a typo somewhere? Yes, there's a typo, that's why. So can we remove that?
That's kind of the annoying thing. Oh, maybe. Yeah, I saw you had another typo somewhere along
Mm-hmm.
that
8,
one. That's kind of
5.
the annoying thing with something with numbers,
Yes.
I'd say.
Wait. It's this one. Okay. Much better. Okay. So now we have undefined reference to this. Probably because I didn't rename it correctly. Okay, and we still call apply mask. And here, okay, good. Okay, not a single warning. Everything seems good. Let's see about Git. Okay, so commit your work, and then I'll write um, the UART test quickly before we all go to bed. Maybe not all of us. Who here, for example, is in the US and still has some shiny sun outside? Because we're in Europe here, and it's just completely dark already. Driver, yeah. Okay.
The make file.
So you can push it and create a merge request or a pull request. I don't know how they call them on GitHub.
What about the make file though? Or is that also?
Oh, you didn't commit everything.
Oops.
You have to. So git commit a for everything, amend to change the last commit, and you can just save and all the current modifications will be added to the last commit.
Seems like it worked. I think. Yeah. Okay. I'll be working on my
Okay.
machine then.
So I'll close your side. Um, I'll close your consoles here. Okay.
Okay. Hang on, I need to lose focus. On the thing. Oh, I already did.
There was a control character, probably. Okay. Oh shit, I've been running that all the time. I forgot it completely, like, this is the code that I've just been running all evening, okay? And this actually consumes electricity for nothing.
Oh.
And you can see here that, yeah, it's all green. Like, this is a 6-processor machine, so not all of them have been running uselessly, but still. We'll change that by with an HLT instruction, by the way. Okay, so I'll start looking at how to implement those changes in your driver while Metal Snake is creating the pull request. And to do that, I'll just, mindlessly rely on my previous implementation because it's late and I don't want to think. So how does this work? Enable interrupt. Okay. So we register an interrupt handler. Okay, and here we write. So I really don't need that. That's not the point. I just want to write this here because this tells UART to actually enable interrupts on reception. So,
Made the pull request, by the way.
okay. How is our code organized? We set up the CPU first and then UART, which means that here we already have everything set up to to receive interrupts. So the register, which one is it? It's the IER, and the IER is 1. Okay. Okay. And what do we write in this? IERRX, okay, which is just 1. Okay, you can see it here. So basically we write a single bit in the interrupt enabled register, I suppose. Each bit here controls a single type of interrupt, depending on like event categories. And normally actually this should be enough, right? So here what we want to do is use the I8259 module, which we don't have yet. So the pull request is done, you said, right?
Yep, should be.
Okay. So pull request, okay, merge, confirm, done. Okay. And so here, remotes. Okay. I'm gonna pull from GitHub the master branch on GitHub. Okay. And this way I get the changes from Metal Snake. Okay. And I should have my local modifications, right? So here, now that I have this, the only thing I need to do is tell the PIC. So now I'm in the point of view of the user. So I use your header with your public interface, which currently has no comment, but I'll take care of that. And I want to enable an RQ. And here I know the RQ because it's like we could create a list somewhere to have all the RQs like we have the vectors, the interrupt vectors. We could do that. The difference here is that usually for the hardware, either it's provided by a CPI, so basically it's plug and play, or it's fixed, defined by the architecture, in which case you don't really risk conflicts as long as you comply with the specification. So yeah, actually I don't really care about that because it's just a test. Let's see which RQ is used here. Oh yes, it's here. So 4343. Okay, so these are the interrupts, which means the first one uses interrupt 4. Okay. So enable RQ again. Basically 4, right? Let's build. Let's run it. Okay, it doesn't work yet. Oh, we forgot one thing. But I don't think it's a problem. We forgot to implement the end of interrupt function, but that's okay, we can do that next time. So here, for example, on PIC1 we have 0, and on PIC0 we have 1. Wait, we want the... which one is it? Oh, that doesn't work at all. Yeah, that doesn't work because we forgot to call it here. Okay. Is that better? This looks better. See, this is the IMR word. And here, EB, like if we dump that, so this is bit 0, okay. Bit 2 is enabled, allowing the slave, and this is bit 4. So it is enabled normally. Let's see.
Nice.
Okay, still doesn't work.
What about
Uh,
the global interrupts?
what?
Or is it that global interrupting?
Oh yes, I forgot that. You're right. Let's have it here actually. You're right. So like Metal Snake just said, um, this is what you have. This is your model. It's not really what you have, but um, it's a very good model, and we just took care of that, but we didn't enable interrupts here. And the whole chain must work in order to have your handler called. So this is what I just did. Um, did you touch something?
Oh, hands off the keyboard.
I'm not sure why it wasn't receiving my inputs anymore. Okay, I forgot to compile it actually, I think. And we have an interrupt. Great.
Nice.
So currently what we don't have is a handler. So basically here, we're never going to call that directly. What we're going to call instead is something like CPU set handler, something like this. And the CPU module is going to change the IDT so that the correct handler is called. And we're going to pass a function here that will be used as a function pointer on the other side. And that address is going to be written in the IDT. So not directly actually, because you need some assembly between the two. But except for that, the code jumping to that handler will be very small, a very thin glue of assembly. And then once the IDT is set, we're going to enable the interrupt controller to redirect it, like to have that complete chain from the device to the interrupt handler on the processor. And then what we'll need to implement is the end of interrupt function so that we can see here, something like this. We'll have an end of interrupt with the RQ given. And the handler, so maybe in CPU or maybe the handler in this file, for example, the handler passed as an argument to this function, will call this end of interrupt function when it's done. Or actually, it's probably going to be done pretty early because usually what you do is that you acknowledge the interrupt first to minimize latencies, and then you handle it. If you don't do that, you risk receiving a new interrupt while you're servicing the previous one, and you might lose it. So usually,
Yes.
especially when you have edge triggered, like if you have level triggered, the
Yeah.
level is going to remain high or low depending on your polarization until you acknowledge it. So that's what level triggered is good at, remembering that there is an interrupt. But if you have edge triggered and you don't have an interrupt controller that remembers that keeps a flag of pending interrupts, and you acknowledge too late, you may lose interrupts. And sometimes it's unavoidable. So what you do is that you actually ask the hardware, do you still have data pending? Do you still require me to do some work? And and so you'll have like a loop in your interrupt handler that will continue until all data from your device has been processed. So interrupt handling is quite a complicated subject. I'm not going to go too much into the details. I'm just talking about it, randomly sharing some experiences I have with that. Um, but basically, yeah, we're almost done. We're not completely done. It was a little harder than I thought, as is often the case. But yeah, we have an interrupt. Like here, basically, nothing happens until I press a key. So that's what we wanted. That's what we have. If I press the key a second time, nothing happens because we don't have this end of interrupt function that I just mentioned. So next time we'll work on that. And
Um,
what
I think
else?
on I think on the edge versus level interrupts as well. If you clear the flag as it's still on the high level, if it's level triggered, and you clear the interrupt basically, or the flag for it, um, I'm not quite sure in which cases this works, but in some cases it fires the interrupt over and over since it's still on that level. So
You mean if you do it too early?
if you clear the flag while the pulse is still high, essentially, or low, depending on the polarity, of course. Uh,
Let's assume high means that there is a pending interrupt.
exactly, yeah. So at the start of your pulse, you have an interrupt, or before then, you have an interrupt, and you clear it uh, fairly quickly
Hmm.
while it's still high.
Okay.
It then will see the interrupt as if it's high again because you've cleared the.
Yes, but that's okay. You will have a new call, your handler will be called again, and it must be resilient enough to see that it's a spurious wake up, that it basically
Okay.
has no work to do. This is one case that you may need to handle in your interrupt handlers, yes.
Yeah.
On
Yeah.
x86, for example, legacy interrupts may be shared. You can see that actually even modern ones, but modern ones are much more smarter about that. But you can see here that the same interrupt can be used for multiple devices. Um, it's usually not the case. I don't have a machine here where I can show you that, but for example, you might have, especially for all devices, you might have shared interrupts. So when an interrupt is raised, all drivers are called in a chain, and you don't know which one is actually going to do the work. So they need to be prepared for that case, that they have been called, but there is nothing to do.
Yeah.
So
Okay.
it's not that simple. It's full of tricky stuff, tricky things. But here in that project, we'll keep it simple. And so that basically concludes the development. I'm going to just keep it keep the screen like this so that you have a look at the actual work that was done and the sweat. Okay. And yeah, I'm going to fix that very quickly, but I'll
Oh,
do
of
that later, along with the comments.
course, you have it. Yeah.
So yeah, guys, if you have questions, if you want to discuss things, if you want to like, is there? Yeah, there are new people here. Hello, Zerium. So Mousex says I'm off to continue my MOOC catalog. Thanks for the stream. Yeah, you're welcome. Sorry about the delay. Um, so Azerium, if you're still here, or other people, who's new today, and who is discovering like this project and maybe enjoying low-level programming, but at a fairly simple level. And if that's the case, well, even if it's not the case, what did you find interesting, like during this stream? The most interesting thing, the most like something that surprised you. If anyone wants to answer. If not, well, it's midnight, so we might just end the stream early. Well, early, not as late as if we discuss. I was
Yeah.
assumed to be the stream troll 2 streams back, so now not. Oh, that's you. I forgot your name. Sorry, I have a very bad memory. Welcome. I missed you. I was actually wondering why my nice troll was, because I don't know. People, yeah, people are shy. People don't want to troll. I mean, the nice kind of trolling.
Banter, essentially.
So yeah, here I think the choice of having an object is actually a very nice choice. And honestly, if I wasn't too lazy, I would probably rewrite my own driver in that way
It
because
does
it
make it
makes.
a lot
Hmm?
more scalable as well, I guess.
Yeah, but we don't need that thing to scale. We know it can't scale. It's
Well,
not like the IO APIX, for example. You don't know how many IO APIX you might have. You know that you can't have more than 2 PICs in such a cascade. So it's not really about scalability.
wrong term for it then. But I mean, it's quite easy to uh, change the type of data that you want to
Yes,
have.
maintenance is easy.
Maintenance,
Understanding
exactly.
the code is easy. Avoiding many mistakes is easy. I agree. Yeah.
Yeah. And for me, just seeing if you go to the OS development page, the sort of example code
Hmm.
they have, and compare that to the setup that's here, this is a lot more readable,
Yeah.
and I
Yeah,
think
but
that's the biggest takeaway.
um, many
Or
developers, many low-level developers are not really trained. Like embedded developers in general are not really trained. I think you won't. Uh, I think you'll agree on that. They're not really trained with like high-level application development paradigms.
true, yeah, a
So
lot of software engineering principles and design aspects are kind of lost on.
yeah, and that's very
And
sad.
yeah,
I have the same problem at work, where they are. So I won't be specific because I've had a couple of missions. So not necessarily in my current position, but and in my current company. But yeah, this is something I've seen many, many, many times. Global variables everywhere,
yeah,
functions named in a way that made it impossible to easily know where they are without a good tool, what they're supposed to do because you don't know the context. Here you have the context in that in a name like that, like it's the namespace. Every time you have a namespace, it gives you some information. It's the controller. It's an instance of the PIC, and it's the right data method. You have something that tells you uh, it's not perfect because the underscore is used to separate both um, namespaces and provides like replace spaces inside method names. So so you have to guess. There is a bit of guessing, but it's very easy to know in which file it is. It's very easy to quickly see that these are methods of a single object, and you actually have the object here always as the first argument to match um, expected expected practices of having the this pointer as the first argument. And in object-oriented languages, it's implicit. It's always like it's not even the first. It's like argument zero. You don't even see it.
mm,
Uh, it's like it could be written this way: master right command something.
mm-hmm.
So this is what I would call argument zero.
Yep,
And it's very difficult to maintain. Here we have how many lines do we have? Not even 200. Like it's really small. Not even 200 lines for this. Okay, we'll have 200 with the end of interrupt, but that's it. Imagine you have 50,000 of those lines. And here
mm,
we have less lines because we have an object, so a lot of code is made common by that. 50,000 lines of code that is duplicated with global variables is, spaghetti code. It's really unmaintainable. The only way to maintain that is to rewrite it, and this is I've done that so many times. So this is why I personally worked on those rules and methods a lot because I'm so lazy. You know, uh, I think you probably have heard that developers are lazy people, uh, but usually it's misinterpreted. It's misinterpreted in that they don't want to work. Now here, I just don't want to do useless work, and unfortunately, a lot of the work is so useless when you know how to do things right that, yeah, it's a shame.
yeah,
It
yeah,
must cost so much to the industry on the largest scales, like really millions, tens of millions, perhaps more. I don't know. It's huge. So yeah, and where did I read that? I think it's the Mythical Man Month. Yeah, I still have it here. Communication, maybe? Oh, yes, the surgical team. Brooke, the author of the book, uses that good programmers are generally 5 to 10 times as productive as mediocre ones. And this was in 75. I would say that today it's even a lot more than that.
Mm.
So if you're an embedded developer, or if you're like a hardware developer but who writes drivers for what you produce, and you are able to provide code that looks like this, um, it's become like in Linux, it's become mostly the norm because Linux forces you to have that kind of interface. Like you will have to register a structure with the right function pointers in it, and you will have to write so function. You will need to provide functions that match the types that you need to provide. So basically, you provide callbacks, and these callbacks are called, and they need to be called with a special set of arguments. So you don't have a choice here. You are forced by Linux to do it right, which is very good. It's really good practice. So in Linux, it's not too much of a problem usually. Like you need device instances, you need to look them up, you need to identify them clearly, you need to isolate all the resources. Many resources, not all of them, but a lot of resources are really specific to devices. So the kernel takes care of that and forces an interface that you must abide to. But on many smaller projects, that's not the case, and unfortunately, it produces abominations and monsters. So, not here to start a flame war. Hmm. Oh, that's okay. Um, if there ever is a flame war, like a true flame war here, I would imagine that the first 5 to 10 minutes would be like I would probably participate in the war because it's fun, and after some point I would say, okay, it's that's enough, come on, calm down, kids, and if people don't calm down, there is the almighty ban hammer that comes and settles down everyone involved, because it's uh, one perk you get as a streamer is that on your stream, on your chat, even if there are only 10 people, you're always right. Because if you think people are wrong, you can just ban them. So, hello, Captain
So
Craft. Nice to see you here. We're just about to end, actually, unless I'd really like to talk a bit if people have questions, but if you don't, I'll be slightly disappointed, but we'll have to move on anyway. What could we talk about? I really think we covered it all. So memory allocation next time. Normally, well, we'll
I
finish the
was about to
pick
say,
quickly,
yeah.
and then we'll move to memory allocation. But we will probably talk about that off stream.
So
I don't know what to ask questions about. Yeah, I know. That's probably a problem for many people here. Um, so yeah, my question really was, but it was about the code. So if you weren't there earlier, it's probably no use. Um, Now I wanted to know who here is new, but I guess not many people are new. And I wanted to know them better, like who is a student, who is interested by the kind of educational projects we're doing right now, uh, who has actually worked with it and learned a few things about it already. That would be very nice to know. I have a question. Why does my probe fail when running normally or in CGDB, but it doesn't fail when running via GDB? Mhm. So that's called a Heisenberg, and there is no silver bullet answer for that one, especially since you use ptrace. Because I know it's about, I expect it's about Lisa, so I imagine you use ptrace, and I can imagine that if you use GDB, which also uses ptrace, you might have weird interactions between GDB, the kernel, and your own program. And unfortunately, I can't answer that. I don't know ptrace enough. Like, I actually don't work on Linux that much. I haven't worked on the kernel for years. And yeah, no, I don't know. And even GDB, I've actually ported GDB to other systems, but I have never used it. I mean, the code, I've never. looked at the code for Linux itself ever because it just works. You're useless, I know. But at the same time, I'm not paid. Uh, I don't know. I have no contract to be useful, so I can just be like many other Twitch streamers and just, be useless like them. Uh, the same way. Yeah, I'm sorry, Captain Craft. I'm sorry. You'll be refunded. What would be the appropriate answer for that with emotes? I have no idea.
I don't speak emote that well.
That one maybe? Yeah, no, I don't have any emote that would convey the meaning clearly. Um, so yeah, let's see. I see new names on the other hand. I see Cashpo, I see Gedyuko, and hello to all the lurkers who kept lurking and didn't say hello. I see an happy hobbit quite often. I don't know who you are. Anonymous Grey, hello. Cray7, I don't remember your name either. So yeah, guys, don't be shy. I know you're not here for the music today. I know that.
It's a shame, but
Yeah, but it makes like the really good thing is that it makes the videos completely uh, audible,
yeah, you
hearable.
don't need to you don't need to worry
Um,
about royalty-free stuff,
yeah.
basically.
So since I've created a collection, by the way, you can see in the collections that there is it's like a playlist of all the videos that we make about that project in particular, and
Oh, nice.
it's good. It's good to know that people will actually hear everything, and that's actually not the case because the last one was me alone. So there are two voices. Yes, Captain Craft, we're doing that with Metal Snake, as the title says. So today was Metal Snake. Well, yeah, we both coded it. So he's a student, and we make sure that the complexity, the level, the general level of the project remains accessible to students. So that's a very good way to like having a student be part of the project is a very good way that it's actually uh, uh, not too complicated. Would actually never listen to classical music normally, but it oddly fit perfectly the previous times I popped in. Happy. That's because, like all music, there is good classical music, you know, that you don't fall asleep to. It is fun, yeah, really fun. I'm having a lot more fun now than coding my other kernel. And by the way, guys, you may have noticed, maybe not, I don't know. I'm not very motivated these times. I'm not working on X15 much, and only during streams. And I like the frequency of those streams uh, has been reduced. So yeah, currently I'm yeah not coding much on it. But X1 is very fun to work on. I preferred writing documentation for X1 rather than playing with registers on ARM with X15. That's how it is. But both will progress eventually. Both will be finished eventually. X1 is probably going to take more time than we think because, as usual, in project management, you should always expect things to be late, like at least twice, sometimes
Today,
three times. So
today I heard something about uh, planning project or project management,
mhm.
and how long it would take. And I don't know who was that said this, but take a realistic planning and add it or times it by pi. That's your
That, that's a very good one. I would say by E personally, but yeah, who cares really? E I, pi,
yeah.
whatever. Yeah, multiply by I. Yeah, that's a good one. That's a very good one. This way, it's not realistic anymore. That's how people should understand planning. No, it's not realistic anyway. Used to be a few reverses streaming, but I guess Twitch has banned it. Oh, reverses. Oh, I see. Haven't seen one in ages. So wish there was a platform for streamers doing that sort of stuff. Yeah, yeah, I
There
got
is.
that. Yeah.
Well, hardware. I know there is some hardware reverse engineering at least, like electronics streams every now and then,
Mm,
but they're not around very often.
that's sad. Crazy.
It
Yeah.
is. Yeah.
It really depends. The problem is that Twitch probably doesn't want to make any effort in checking whether it's legit or not. So
Yeah.
by default, just uh, disallow it for convenience. And unfortunately, I understand why. Okay, so guys, we're going to end the stream. Thanks for watching. Hope you enjoyed. Hope you learned a few things. Hope you'll be there next time. So when is next time? Yeah, that's the question, right?
Yeah. I should have more time coming up.
Oh,
I
really? That's good
um
because
right
we're
now.
getting late.
Yeah. Um. See.
So next week, maybe,
Oh,
probably,
definitely next
definitely.
week.
Okay,
Just I'm guessing more early in the week. I think.
okay.
Um.
Let me check. I don't have anything planned for next week. No,
I have
that's okay.
exams. I have exams basically this or the next week, which I only have one of, so there's not that much going
Okay,
on.
you'll tell me when, and I'll update the panels below the stream.
Exactly. Yeah. Yeah.
Okay, so we
That's
can't
the
we
way.
can't tell you an exact date right now, but we'll be streaming early next week. We don't know when exactly. Around 8:30 CET now, so Central European time, because it's not summer anymore, and we do have that here. And that's it. Okay, bye. Enjoy life. Bye bye.
Good night.